Hey everybody, welcome back to finally part 3 of talking about these sequences in context. Here we are with Augustus again. We're going to talk about a different problem. And not saying it's really complicated, but it's a little bit different, okay? So let's read this thing and see if we can get our heads wrapped around it. It says, Augustus decides all candy isn't healthy for him. But if everyone had just a little, it would be okay. He decides that he will share his candy with everyone at school. And when he has a pile of 100,000 candies, he generously plans to give away 60% of the candies that are in the pile each day. Although Augustus may be earning more candies for doing his homework, he is only giving away candies from the pile that started with 100,000, so he's not that generous. How many pieces of candy will he have left on day 4? All right, so let's have a little talk here about what's happening here. It says he's going to give away 60%. They want to know how much he's got left. So there's a difference. Giving away 60 means you have 40%, right? Because there's a total of 100%. So if you're giving away 60, you're going to keep 40. So if we started working with that 60%, we'd be showing how much candy he's given away, but they're not asking for that. They want to know how much is left, so we have to be careful. Let me pull up this board here, and we'll see if we can spot this sequence. Let me clear this thing up from the last one we did, and maybe we'll make us a little chart. So we know the days are ends, right? Again, so this is the number of days. I'll tell you what, let's write that in just so it'll be more clear, because this one's a little bit more confusing. All right, so we got days going up here. All right, and then we're gonna have, say, candy in this column. All right, on day 1, he's going to give away 60% of his candy. He's starting with 100,000 pieces. So you would have to calculate that, right? So we'd have 100,000 pieces of candy, and we want to know what is 40% of 100,000. Now, you guys, when you hear the language of, that means multiply. 40% of. You remember, you multiply by 0.4. Move your decimal 2 places. Multiply by 0.4. So there's obviously going to be 40,000 pieces of candy left after the first day. And I'm going to show you a trick in just a second on that machine that makes it quick. So we get 40,000 here. That's after giving away 60,000 pieces, right? Day 2, he's going to give away 40% of that amount of candy. So here's a way you can work this out in your calculator pretty quick. So instead of re-entering that data, put times. Now see how it says answer there? It's multiplying your last answer for you. Now we're going to go by 0.4 again. And we get 16,000 pieces times 0.4. And so there's the first, second, third times 0.4 again. And there's my 4th day. So I'll have 2,560 pieces left after 4 days. So let's go fill in our chart. Now I was just trying to show you how you can make a shortcut with this calculator and not have so many keystrokes. All right, so let's go back in here and fill this thing out. So we said on day 2 he'd have 16,000. Day 3 he had 6,400. And day 4, which is the day in question, he had 1,024. Okay, now that takes care of the first question. How many pieces would he have on day 4? Well, we got that. Now, we were careful not to use that 60%, but it's complement, I guess you could say, of 40%. It says, model the amount of candy that would be left in the pile each day. So this is where they're asking for an nth term formula. That's what that means. So when we get ready to look at that, I don't know if you realize this, since we're multiplying by 0.4 to get to the next term, we already know R is 0.4. It is. And if you were to take these things and divide them, you will get 0.4. because we multiplied by 0.4 to get from 40,000 to 16,000. So our formula is not going to be too hard to write. We'll write f of n equals 40,000, that's your f of 1, times 0.4 to the n minus 1. And that right there will make predictions in this sequence. Now, notice this is a decreasing geometric sequence. That's fine. When someone says it's growing exponentially, people have a tendency to think that it's blowing up and getting huge, but that can mean that it's going down exponentially and decreasing, and that's what this one happens to be doing. Let's see. We got our model made. Now it says, how many days will it take for the candy to be gone? That means there's nothing left in the pile. Now, on our Math 1 level, we're going to have to do some guessing and checking with this, because what we really want to know, when's the pile going to be gone? That means, when is this number going to be 0? And remember, that's your output, f of n. And this is days. So to solve that actually would require us to know a little bit more than what we learned in Math 1, but we could do a sort of an estimate. Now, when we start talking about whole days, that's the way we'll have to treat this. There are no days in between, so let's just do some guessing and checking. And what I would start with, I mean, this is completely shooting from the hip here. What would it look like in 10 days, right? So f of 10. So we're going to attempt to do some guessing and checking with this thing. So we have 0.4, and I'm not going to write this down because, oh, that looks so bad. 0.4, parenthesis. 10 minus 1 is a 9. Okay, so we're going to compute this real quick. And we're going to clear that stuff out of there. Now we want to write 40,000. Oh, one more 0. Times 0.4 to the 9th. This is after 9 days. Well, he's still got 10 pieces of candy left. So another thing you can do, second entry, put your entry back up there, then you can just go back in and edit. So I want to know what happens in, that's 10 days. 11 days would put me at 10 there, wouldn't it? Because it's n minus 1. We got 4 pieces, so that's not going to be it. He's not out yet. Bring it back. It looks like that guy might need to be an 11. So this model, okay, so he's got 1.6 pieces of candy left on the 12th day, because remember, we're ahead by a day with his numbers. And just to be clear, let's do it one more time and see what happens on the 13th day. Oh, doesn't even have a whole piece. So I don't think he's going to take that last piece and start to divide it up and partition it. Because in fact, this, if we keep going with this, this really never gets, well, they might say at infinity it gets to 0, but really it's going to get smaller and smaller and smaller because he's dividing it. So it looks like day 12 would be our best answer. This is actually day 13. So it happens at day 12 he has 1 piece left. And so that's how I would answer that question. All right. How many days will it take for the candy to be gone? About 12 days, right? Okay, so I'll fill these notes in later. And to wrap this up, I just wanted to show you this box, and this is the box I want you to put in your notes. Modeling exponential progressions. And I think it's important to call these exponential, because later when we study exponential functions, you're going to see us doing very similar things, except maybe not thinking of it as a sequence as much. It says a geometric sequence is an exponential progression. Terms are found by multiplying the previous one by a fixed number called the common ratio R. Well, we already knew that. That's actually part of that other box, our other definition box. And then we'll go through the quick summary of the steps here. It says carefully read the text and write the first few terms. We did that, and it's a smart thing to do. It's just wrapping your head around the context. It says positively identify the sequence as arithmetic or geometric. Yes, that's what you have to do. You can't make a model unless you know what type of data you're modeling. It says if the terms are changing by a percentage, this is important. I put it in blue so it'd be different. Then it's an exponential progression. It's geometric. If it's changing by a percentage, it's geometric. All right, so don't get those confused. Anytime they use a percentage and it's changing on a daily basis, monthly basis, weekly basis, it's a percentage. I mean, it's geometric. And I said finally, look for the words that signal that you're multiplying from term to term. That's how you spot one of these exponential progressions or a geometric sequence, okay? Anyway, that's it for this video. I know it got a little bit long, and I hope that you find this helpful. There's 10 problems to do in Delta Math concerning these things, and I will see you on a y = mx + b review.